Welcome to qnawire.
Hi everyone, so what we have is the maximum flow rate of a standard shower head. That's 13.3 liters per minute. We know that a new shower head has a flow rate of 10.5 liters per minute. What we're assuming is that we have a family of 4 who take 5 minutes per shower. And we know that the city water is coming in at 15 degrees C, is heated up to 55 degrees C, but then is chilled back down to 42 degrees C. What we're asked to find is the ratio of the hot to cold mass flow rates of the water, and we're also asked to find the energy that's saved by using this new shower head. So the first thing we're going to do is just take a look at our properties. We know that the density of water, which is incompressible, is 1 kilogram per liter, and the specific heat of water is 4.18 kilojoules per kilogram degree Celsius. Now what we're going to do is we're going to actually take the mixing chamber, which looks like this. So basically this is your mixing chamber. You have cold water coming in, you have hot water coming in, and then you have your mixture coming out. So this is going to be 1, 2, and 3. And that's going to be our system. So what we're going to do is we're going to do our mass balance first. So we know that the total mass coming in minus the total mass that's leaving is equal to the total change in mass of the system. Now we are going to be operating at steady state conditions, so the total change in mass of the system is going to be equal to 0. Therefore we know that M in is equal to M out. And what this means is that M dot 3, which is our mass that's leaving, is equal to the mass that's coming in from the hot water or from the cold water, plus the mass that's leaving from the hot water. Next, we're going to do our energy balance. So we know that the energy coming in minus the energy leaving is equal to the total change in energy of our system. Now again, we're at steady state conditions, so the total change in energy of the system will be 0. So we can see that E dot in is equal to E dot out. Now we can write this out in terms of its constituents and say that M dot 1 H1 plus M dot 2 H2 is equal to M dot 3 H3. Since we're going to be assuming that work, heat transfer, and kinetic energy, potential energy is negligible. So now what we can do is we can actually combine this energy balance with our mass balance. So recall that in our mass balance we left off with that M dot 3 is equal to M dot 1 plus M dot 2. So what we can do is we can actually go ahead and plug this expression in right here for M dot 3. And what we have is M dot 1 H1 plus M dot 2 H2 is equal to M dot 1 plus M dot 2 times H3. And what we can do is we can actually rearrange terms again and get M dot 2 H2 minus H3 is equal to M dot 1 H3 minus H1. Now what we can do is we can get a ratio of M dot 2 over M dot 1, which is our ratio of hot over cold, and say that's equal to H3 minus H1 all over H2 minus H3. And this we can write in terms of temperature and just say that this is Cp times T3 minus T1 all over Cp T2 minus T3. As you can see, our Cp values cancel out, and all we're left with is a ratio in terms of temperatures. Now we do know T3 to be 42 degrees Celsius, T1 to be 15 degrees Celsius, and T2 to be 55 degrees Celsius. So plugging those quantities in, we see that a ratio of the hot mass flow rate over the cold water mass flow rate to be equal to 2.08. And that is one part of our final answer. Next, what we're also trying to solve for is the energy that's saved per year from using the low flow shower heads. So what we can do is we can calculate the actual volume flow rate that's saved. So what we can do is we can say that is V dot saved is equal to the difference in the volume flow rates of each shower head. So we can just call that delta F times basically the amount of time that is spent showering. So we know that's 5 minutes a person times 4 people, since we have 4 people in the family, times 365 days a year. And what this gives us is that we save 20,440 liters over a year by using these new shower heads. Now we can translate this into an m dot that's saved. So we can say that m dot saved is equal to rho times v dot, and knowing that the density of water is 1 kilogram per liter, this gives us a total kilogram saved of, again, 20,440 kg per year. Now what we can do is we can use this m dot that's saved and multiply it by the specific heat and change in temperature to find the energy that's saved. So we can say that E saved is equal to m dot saved times Cp times delta T. And this gives us, we know that the m dot is 20,440. We know C to be 4.18 kilojoules per kilogram degree Celsius. And our delta T is going to be our final exit temperature, 42 degrees C, minus the incoming temperature of 15 degrees C. And this gives us a total kilojoules per year saved of 2,370,000 kilojoules per year. Now this we can translate into kilowatt hours, and this is actually equal to 641 kilowatt hours. And that is how much electricity that we have saved by using the new flow shower heads. That's our final answer.